Okay, thanks, David. So I'll get started. So yeah, the talk's titled GPU Programming with CUDA. Let's just check this is working. Yep, no, it's okay. So just to give you an overview, so I'll start off describing why we're interested in GPU programming and why we have a need for CUDA, the programming language, what CUDA is. I'll give you a full introduction to CUDA, talk about the different aspects of CUDA that allow you to program for the GPU. CUDA kernels, decomposition, memory management, and I'll also describe CUDA for both C and Fortran. So you can program CUDA in C or C++ and Fortran. So I'll explain that as I go along. Okay. So motivation, first of all. So this is a slide from NVIDIA. So the presentation focuses on NVIDIA GPUs. These are most widely used at the moment in terms of the different types of GPUs that are available for scientific computing. But of course, there are other types of GPUs. In particular, there's AMD GPUs, which are very high performing as well. The reason that most people use NVIDIA is because the programming environment is a little bit more simplistic and easier to use. But some people do use AMD. This talk is focusing on NVIDIA, but a lot of the concepts, the ideas are similar for AMD as well. So this is a slide taken from NVIDIA that just shows what the performance advantages of GPUs are over regular CPUs. So it shows you two graphs. On the left, we have performance, computational performance, and on the right, we have memory bandwidth. And the green line is GPU, high is good here, and the blue line is CPU. So you can see that the performance of the leading GPUs has increased more rapidly than the performance of leading CPUs over the last few years. And we're in a situation at the moment where GPUs have this, in terms of the peak performance, they have quite a significant advantage over CPUs. And this is true also. A lot of scientific applications are sensitive to memory bandwidth, and it's true also that GPUs have a memory bandwidth advantage over CPUs because they use graphics memory rather than regular DRAM memory. So GPUs have a peak performance advantage over CPUs, but the reason that not everyone's using GPUs is because they're more difficult to use than CPUs. And they're not suitable for all types of application. So I'll try and explain that as we go along, and explain how you can adapt your codes to use GPUs. So what you can't do is you can't just take your code that's written in C or C++ or Fortran or whatever and compile it for a GPU. If you do that, what would happen is it would end up just running on the CPU. If you have a system that has GPUs, it also has to have CPUs in it. It's called a heterogeneous architecture or an accelerated architecture. So you have a combination of CPUs and GPUs. And if you just take your application and try to run it without adapting it, it will just end up using the CPU as it would have done anyway if there was no GPUs in the system. So what you need to do is you need to program your code to offload parts of it to the GPU architecture, to the GPU, which then these parts of the code can then be accelerated by the GPU and make your whole program run faster than it would have done if you hadn't done that. So the CUDA programming language provides the syntax that allows you to do this, that allows you to take advantage of GPUs in the system. So it's usually the case that for scientific codes that most codes have a relatively small fraction of the source code, like lines of source, that is responsible for a relatively large fraction of the runtime. We call these key computational kernels. For example, if you have a code that does time stepping, for instance, your loop over time steps will be the one that takes most of the runtime. So what we're interested in doing is just concentrating on those parts of the code and trying to offload them to the GPU, to get them to run on the GPU so they can run faster than they would have done on the CPU. So what we need to do is to define those parts of the code, or specify those parts of the code that we want to offload. We call these kernels, and CUDA defines the language extensions that we can use to define these kernels. So CUDA it provides extensions to the traditional languages that we're used to using, in particular C and C++. And the idea is that we can offload these kernels to the GPU. The GPUs, we don't have time to go into the details or a detailed overview of the GPU architecture. We'll get to that. We'll touch on that a little bit. But the key thing about GPUs is that they have many cores, and therefore they run many threads. So what the kernels do is they execute in these using multiple threads concurrently on all the cores of the GPU. But a major complication with GPU architecture or GPU accelerated systems is that they have a separate memory space in CPUs. You've got two, you end up having to manage two separate memory spaces, one in the CPU and one linked to the GPU, and the programmer is responsible for transferring the memory between the CPU and the GPU. And CUDA provides the syntax to allow you to do that as well. So this bullet point here was concentrating on C and C++. And the reason is that CUDA originally, or the version of CUDA that you download from NVIDIA's website, is specific to C and C++, so it's an extension of C, C++. But what about Fortran? A lot of scientists use Fortran. Well, at some point, NVIDIA teamed up with PGI. They're a compiler company, a compiler vendor, and PGI developed a commercial version of CUDA Fortran. So this is very much based on CUDA C, following the same methodology really, but it's for Fortran. It's extensions of Fortran rather than C. As we'll see, it's very similar to CUDA C. And actually, a year ago, NVIDIA acquired PGI. So PGI is now part of NVIDIA, but they've not completely integrated the Fortran into their software release. They've kept PGI as a separate outward-facing company. So it looks very similar as it did before. You still have to buy this CUDA Fortran compiler from PGI rather than get it free from NVIDIA. Okay. So this picture just gives you a sort of cartoon, if you like, of our hardware. So we have a CPU in the system where we run most of our program, most of our application. And then we identify these key computational kernels that we want to offload to our GPU. These are the things that take most of the time in our application. And the idea is we offload these so they can take advantage of the many cores in the GPU. And then, of course, we need to manage things. We need to manage communications between our CPU and our GPU. We need to transfer data, etc. And we have a bus in the system that allows us to do that, and that's the PCI Express bus. So GPU stands for General Purpose Programming and Graphics Processing Units. And it uses the stream model of computation. So what is the stream model of computation? Well, this picture tries to illustrate it. So the top part of the picture here shows you the serial or traditional sequential model of computation. And what you should think of is these blue boxes as being data elements, and then the red arrow being a thread of execution. Okay, so in a serial or traditional sequential programming model, you have a single thread, okay, so it's sequential, that just iterates over all of your data elements. Okay, so this would be implemented using a loop in your code. Okay, the idea behind stream computing is that you can decompose this data set into what we call a stream of elements, and then we can run a separate thread or computation. So we can run if this idea is that we can do this when we want to use a single computational function, or what we call a kernel, on each element. Then if we can decompose our data structure, then we can use multiple threads to run in parallel with each other. So we can, instead of having a single thread, we have these multiple threads, each of them performing the same operation, but on a different data element. Okay, so what we define a thread as is the execution of a kernel on a single data element. And then, of course, we have multiple cores in our GPU. The idea is we can map these threads to the cores, and then we can run them in parallel on the GPU. So we've got many threads running in parallel. Of course, this is not suitable for all types of problems. It's only suitable for those problems that are data parallel, that we want to perform the same operation across a data set. Okay. So this just shows you, zooming in a little bit on the GPU architecture. So this is what a GPU chip looks like. Again, a sort of cartoon. So if you look at the left-hand picture, you can see that we have this GPU. And the key thing about a GPU architecture is that it's partitioned into these things called SMs, or streaming multiprocessors. Okay. And then each SM is itself partitioned into cores. Okay, so we have this two-level hierarchy in our GPU. We have multiple SMs, and each SM has multiple cores. And another key thing about the GPUs is that the number of SMs, which I've showed 4 on this cartoon, but the number of SMs and also the number of cores per SM is not fixed. Okay, there's not a magic number that all GPUs have the same number of SMs or cores per SM. This will vary across generations and also across different products within the same generation. Okay, so what we want to be able to do is to program for this architecture, but not in a way that we're tied to any specific version. So we want to program in a way that can take good advantage of this two-level hierarchy, but without being fixed to any specific numbers for a particular architecture. So what we do in CUDA is we abstract this architecture as what we call a grid of thread blocks. Okay, so in CUDA language, we have the terms grid of thread blocks, and where the multiple blocks, these blocks in this grid map onto multiple SMs. Okay, so the SMs are an abstraction, the blocks are an abstraction of the SMs, and then each block in a grid contains multiple threads. So again, thread is a software concept which map onto multiple cores in an SM. So the key thing about this is that when we program in CUDA, we use blocks and threads rather than grids and SMs and cores, and we don't need to know the exact details of the hardware, the number of SMs or the cores per SM. What we do is we oversubscribe. So we give more SMs, we give more blocks than we have SMs, and we give more threads than we have cores. And what GPUs are very good at doing is performing scheduling automatically. Okay, so you give it more work than it can do at any one time, and it will schedule it, and it will be able to switch between different blocks and different threads very quickly. You actually have to do that. You actually have to do this to get good performance. It's not just a case that you want to fill up your GPU. In order to get good performance in the GPU, you actually have to give it more work than it can do at any one time, so it can do this switching. And the reason is, this is getting a little bit more technical now, but the reason is that it will hide memory latencies by doing this. And when one thread is waiting for data from memory, then if it's got another thread to switch in, then it will be able to hide that latency and get good performance. So the key thing is you want to give it more parallelism than it can cope with at any one time, and it will schedule. And then doing this, it means that the same code should in principle be portable and efficient across these different versions of the GPUs, different generations. So I'm going to introduce CUDA properly in a second, but beforehand, I just have to introduce this new type that you have in CUDA, called a DIM3 type. And this is just simply a collection of 3 integers, okay, corresponding to each of the X, Y, and Z directions. So I mean, the reason that it's 3 is that we have 3 dimensions of space, and so what do they call X, Y, and Z? So for many scientific problems, they're either 1D, 2D, or 3D. So the idea is we've got this DIM3 type, which is just a collection of 3 integers corresponding to X, Y, and Z directions. In C, you declare this using the DIM3 specifier, and you can call it whatever you want, and then you can assign values to this data structure as follows, using this syntax here, where you give it some X value, Y value, and Z value, and you declare it. Fortran is very similar, but you use the type syntax in Fortran, and then you initialize using this DIM3 function call. Okay. And we'll come back to that shortly. one more slide here on this. So then if you want to access a component of that after it's been initialized, then in C, you would just use the standard syntax for accessing the component of a struct, the dot operator, to get, for example, the X value here, or in Fortran, the similar Fortran equivalent using the percentage sign. And similarly for the Y and the Z components. So for example, this is a Fortran example. If you have my X, Y, Z values equals dim3, 6, 4, 12, then you would end up giving the X component 6, the Y component 4, and the Z component 12. So if you then access the Z component using this syntax, it would return the value 12. Okay. Right, so I'm just going to now introduce CUDA properly, first of all by way of analogy. So I want you all to pretend that you're not listening to this boring tutorial and pretend you're on holiday in the CUDA hotel. Okay, looks very exciting. So you all check into the hotel, okay, as do everyone else that's in this virtual tutorial. And when you check into the hotel, then the receptionist allocates your room, okay, using the simplest possible mechanism. The receptionist allocates your room in order, okay, so the first person gets room 1, the second person room 2, third person room 3, etc. But the problem is that it gets quite late at night and the receptionist realizes that the hotel is actually less than half full, okay, and he knows how noisy you all are and you're going to all disturb each other, okay, because you're all in rooms next to each other. So the solution is that the receptionist decides that instead of having you in your room I, then he wants to move each of you to a new room 2I, okay, so he's going to basically stride your rooms from the first person should be in room 1, the second in room 3, the third in room 5, etc. So no one's got a neighbour to disturb them. So the problem is, how is he going to do this? So there's a serial solution where the receptionist just gets a pen and paper and goes through each of you and works out, calculates what your new room number is from your old one. Okay, but the receptionist is not very bright and it's taking a very long time to do these calculations. So he decides to use the parallel solution instead, which is he just gets a megaphone and he says, everyone, I want you to check your room number, multiply it by 2, and then move to that room. Okay, so like everyone's just to go and look at their door to see what room they are, get that number, multiply it by 2, and then that's the new room. They can move to that room. Okay, so that's a parallel solution where everyone works out their own room number. So just looking at this in code, this is the serial solution. We just have a loop. Okay, so we're using C here, so we start at 0 rather than 1. But the serial solution is this: you have a loop, and then you have your I is your room number, which corresponds to the loop index. And so you just loop over I, and each iteration you get the result, which is just 2 times I, where I is the loop index. This is of course a parallel loop, so we can parallelize by assigning each iteration to a separate CUDA thread, okay, or in general to a separate thread, but obviously we're looking at CUDA here. So let's look at the CUDA solution, CUDA parallel solution. So there's a few things here that are new. So the first thing to notice is, so this line here, result I equals 2 times I, is exactly the same as what was in our original loop. Okay, this is the body of our loop, but it's not in a loop anymore. It's now in a function. Okay, so we've replaced the loop with a function. We're using this global specifier on our function, and this is just the special CUDA syntax to specify that we want to run this function on the GPU. So this function is going to form a GPU kernel. And also, we don't have a loop, so how do we get our I? Okay, where does I come from if we don't have a loop? Well, we use some other CUDA internal syntax to get our room number rather than from a loop index. We use this built-in CUDA syntax thread idx.x. Okay, so this is the equivalent of you looking at your room number. Okay, so you're now in your hotel room or in the body of this function, and you need to work out which thread you correspond to or what your door number is. So you look up this internal variable. It's equivalent of looking at your door number to work out which thread you are. So this function is now going to be executed across multiple threads. So it's going to be executed in parallel, and each thread will be given a separate thread idx.x. That's again like the room number. So you have to think of yourself as being this thread, and then which room number, what's your room number, or what's your ID, and you get it by looking at this internal CUDA syntax, which will vary across all the threads. Okay, so that's the idea really for mapping our loops to CUDA kernels. So what is this thread idx.x? It's one of these dim3 types, and it's just the X component. Okay, at the moment we're just looking at, because this is an inherently one-dimensional problem, it's just looking at a vector operation, then we're just using this X component. The idea behind having 3 components in these dim3 variables is it allows up to 3-dimensional problems to be dealt with simplistically. So obviously 2-dimensional problems would be matrix manipulations, or 3D problems obviously are very common in science as well. At the moment we're just looking at 1D problems, so that's why we're just looking at the .x component. We'll come back to that. So that's how we define the function. How do we launch it? So again, we use some CUDA syntax, which is these in the red here, these funny brackets or chevrons. What we're doing here is we're launching a kernel. So that my kernel here is just the name of our function that we defined in the previous slide, and the result is just the argument into the function, the data space to store our result. But as I say, we want to launch this function in parallel across multiple threads. So what we do is we specify here what our thread decomposition is. And this is our mapping onto threads and blocks that I talked about earlier. So at the moment, we're just doing the most simple thing possible, which is we're just using a single block, okay? And we're using, and that's why we have this 1, 1, 1. These correspond to the X, Y, and Z components. And again, this is a 1D problem, so we're really only interested in the X component, which is the first one. So the other ones are just 1 by default. The first component, again, we're just saying is 1 here, so we're just using a single block. And of course, we need to then use n threads within that block, where n corresponds to the number of rooms we have, the number of people we have that we're interested in, assigning new rooms. This is the size of our problem. This is a simple way of getting it working, but this is actually not going to perform very well. Oh, actually, I'll come back to why it doesn't perform well, but I'll give you the Fortran equivalent first of all. Fortran is very similar. We have attributes global here instead of the underscore global variable we had in C, and we have the thread idx %x for our Fortran syntax rather than the .x, and we launch it, and it's the syntax again. It's just equivalent here. But it only uses 1 block, so it's not going to perform well, okay? Because, as I say, the blocks are assigned to SMs, so that means we'd only end up using 1 SM on the GPU, so that means all the other SMs on the GPU would just be idle, and they wouldn't be doing anything, so the performance would be very poor. So in practice, we need to use multiple blocks to utilize all the SMs, okay? So that's why the model allows us to do this. So this is an equivalent version that will perform much better because it uses multiple blocks, okay? So now what I'm doing, if we look at the bottom half first of all, I'm setting up the decomposition here. And what I'm doing now is assuming here, for simplicity, I'm assuming that n is some multiple of 256, okay? So n is a large number, that's some multiple of 256. So what this means is that I've chosen that I want to run 256 threads per block, okay? And that is just, why have I chosen that? Well, that actually turns out just to be a good number. For architectural reasons in the GPU, typically the number of threads per block you want to run is some small multiple of 32, okay? So it's going to be, for example, 64, 128, 256, 512 typically. And so what you normally want to do is just choose a number that performs well, and you would probably want to experiment with different numbers to see which one perform well for your case. So you choose the number of threads per block, and then the number of blocks per grid is just dependent on your problem size. So it's n divided by 256. Okay, so say we have 512 as a problem size, then we'd end up using 2 blocks to cover the problem space. For real problems, of course, you won't have things dividing exactly, so you need a little bit more logic in here to deal with that. But that's, yeah, for the purposes of this introductory, we're just going to ignore that. It's easily enough done in practice. So then when we launch that, again, we just launch that using the blocks per grid and threads per block. And our kernel looks very similar to before, but we now need to take account of the fact that we have multiple threads, not multiple blocks as well as the number of threads. So our thread index, our overall thread index is calculated like this, using these other internal variables. It's just a linearization of our blocks and threads. So it's the block index times the number of the block dim.x, just is another internal variable that gives you the number of threads in the block, okay, plus the thread index.x. So this is, again, coming back to the hotel analogy, this is similar to the idea that if you have a hotel that has multiple buildings in it and each has their own numbering system, then you would need to understand what the overall global number of your room was. So to get that, you would need to know what your block number was, or your building number was, plus the number in that building, okay. So, and then that's the equivalent to loop index again, and we can just use it as we did before. Fortran, again, it's exactly equivalent here, so I don't think we need to spend too long on that. So that was obviously not a very realistic example, so let's go into some slightly more realistic examples. One is just vector addition, so you have two vectors and you want to add them together. And this is very similar. So the bottom part here just looks almost exactly the same as before, but we have multiple arguments to our function corresponding to the input and output arrays. And we get our index, our overall index again as before, and we just perform our vector operations. So this kernel is going to run multiple times across the grid of the multiple blocks, each with multiple threads, and each I will then be a unique global index that will determine the element of the vector that's going to get calculated. Okay. And the equivalent for Fortran, again, this is exactly equivalent here. Okay. So let's just make sure we're completely understand what these internal variables are that we've seen. So for the 1D decomposition that we've seen in the previous slide, we just used the .x components. And we had block dim.x, so that took, in our previous example, we specified we wanted 256 threads per block, so this would have taken the value 256. Thread index.x was unique to each thread in a block, so it would have ranged from 0 to 255 in the previous example. This is with C, first of all. We're going to Fortran on the next slide. And block idx.x is unique to every block in the grid, so this depends on our problem size n, and it ranges from 0 to n divided by 256 minus 1. So for example, as I said, if n was 512, we would have had 2 blocks, so it would range from 0 to n over 256 minus 1, which is 1. Okay, so they've had two unique values of block idx.x. Fortran, the same, except because we have Fortran rather than C, our values start at 1 rather than 0. Okay. So, as I say, we can also do 2D or 3D examples. So this just gives you an example of two-dimensional. So here we have some matrix problem that's inherently two-dimensional. Then what we want to do is to make use of the .y component as well as the .x component of these internal variables. And when we launch this kernel, we want to launch it with blocks in both of the x and y dimensions. So what we do here is we are specifying the number of threads per block, what here to be 16 by 16. Okay, so in total, we're going to end up again with 256, which is 16 by 16. But we're now just treating these as a 2D array of threads within this block rather than a single one dimension. And similarly, we want to run launch with a two-dimensional structure of blocks. So we have n divided by 16 and n divided by 16 in the x and y dimensions. Okay, again, where these all divide nicely. And then to access these in our kernel, we're now using the .y as well as the .x components. Okay, so we have a two-dimensional problem, a matrix addition here, Cij equals Aij plus Bij. So we need our i's and our j's, and we get these from our .x and our .y components. This is equivalent to the 1D version, except we're now accessing in 2 dimensions because of a 2D decomposition. One point worth mentioning here is, why do we have them in this order? Why do we use the GI first and then the I? Well, it turns out that to get good performance, we need to have it so that this thread index.x is that to get good performance, essentially what you need is to have that corresponding to consecutive memory addresses or consecutive elements in your memory space. And that's why we've got it laid out like this, but I won't go into that, some more of a technical detail. That's about memory coalescing. Okay. Fortran, again, equivalent, but we're using the Fortran syntax to define our block of threads and then to access our threads within the kernel, to access the internal variables to specify which ID is given to each thread. Okay, so let's skip back a second to show you. So let's look at, for example, this one again. We're doing this vector addition, and we're taking these values, taking these arguments to specify where our arrays are in memory. So you can see there's a star A as a pointer to this array A here. So what I mentioned earlier, of course, is that these have to be, that the GPU has a separate memory space from the CPU. So when we launch this kernel, then we pass this pointer A in, B and C, and this has to point to data in the GPU memory space in order for this to work. So we have to have functionality to manage the data to get it into the GPU space. And I'll describe that now. So the GPU is a separate memory space from the CPU, and the data accessed in kernels must be in the GPU memory. This is actually not strictly true for the newer versions of GPUs where they're more flexible, but I'm not going into that here because in order to get good performance, you typically want to make sure that your data is on the GPU. Otherwise, it will be very slow. Okay, so we're just assuming that it's strictly true at the moment. And we need to manage the GPU memory and copy data to and from it explicitly. So we have functions or library calls in CUDA that allow us to do that. So if you're familiar with the C malloc, which allocates memory in C, then there's an equivalent called CUDA malloc, which allocates memory in CUDA on the GPU rather than the CPU. And similarly, CUDA free will free that releases the memory. So to use this, you would just have your pointer, which you just declare like any other pointer in C, and then you use this call, CUDA malloc, to allocate the memory. So we have to tell it how much memory you want to allocate. So here we're using floats, and we have n of them, and we pass this the address of our pointer so that the system can fill the pointer. It can write to the pointer to give it the address of the GPU memory space. And then when we use CUDA free, we can just pass it the name of the pointer and it will free the space associated with that memory. And also we need to copy memory before and after kernels. So after we've allocated it using the previous calls. So what we have are these CUDA memcopy, and again, these are just analogous to the C memcopy functions. So we need to tell these memcopy functions how much data we want to copy, and also which direction it's going. Is it going from the host to device, that's the CPU host, to GPU device, or is it going the other way from the device to the host? So as I say, the device is another name for a GPU, and the host is another name for a CPU. And it's always the case that the destination comes first. Okay, so that's why we've got the device coming first, where we want to copy the memory. And then second is where we want to copy the memory from. So this is going from the host to the device and vice versa for the opposite direction. Okay, now these are actually very slow, these memory copies relative to other speeds in the system. So they need a major optimization strategy for GPUs, again, which we're not going into in this simple introduction, is to try and minimize these memory copies wherever possible. Fortran, again, is similar, but actually there's some things which are a bit easier in Fortran than in C for memory management. And the reason is just because of the differences with the Fortran and C languages. The key difference is that in C, when we declare our pointer, then, as I said before, it's just a normal C pointer. The compiler has no idea whether it's going to end up pointing to the GPU or the CPU. But in Fortran, what you do is you actually tell the compiler, you specify, you give it this device keyword that tells the compiler this is going to point to GPU memory, and it gives the compiler more power to do operations for you. So if the compiler knows this is a device variable, a device pointer, then it can end up, well, it's able to then just use the normal Fortran allocate and deallocate calls to allocate and deallocate memory, so you don't have to use the CUDA equivalents. And similarly, you can use Fortran array syntax to copy between the host, the GPU and the CPU, as you would do normal memory copies in Fortran. But there also exist the standard CUDA functions that are similar to what we saw for C, if you prefer to use these. And there's also other more advanced ones like asynchronous versions that allow you to do overlapping for optimization. Just a little bit about synchronization. So kernel calls are non-blocking. So every time you launch a kernel, so if you look at this code here, if you launch this vector-add kernel, as soon as that's launched, this is the code you would have running on your CPU, which would launch the kernel onto the GPU. But as soon as the CPU executes this line, control immediately returns to the CPU, and it will just continue to execute the rest of your program. Okay. So what you need to make sure is you put in a synchronization point to stop your code going on to do work with results that it doesn't yet have if the GPU is not yet finished. If you have this CUDA thread synchronized, then it will wait for the GPU to finish. Okay. It may be possible to do something while you wait. If you have some work that your CPU wants to do that doesn't depend on your result, then you can do that in the meantime, so that's overlapping. If you have a CUDA mem copy after your kernel, then that has a implicit synchronization within it as blocking. But as I said previously, there's non-blocking variants for optimization as well. Okay, so that's synchronization between the CPU and the GPU. What about synchronization on the CPU, on the GPU itself? So you have, let's first of all think about the multiple threads that execute within each block. These can synchronize using this sync threads call. Okay, so some algorithms you want to be able to communicate between the different threads in a block. For example, if you're doing some global operation. So you can do that using this sync threads call. So to give you an example, say you want to pass a value from one thread to another thread. So these values might exist, for example, in the registers of each of the threads. Then you could use some some memory space that's shared between these threads that exists on each SM to pass that value. So what you would do here, for example, you could say is if thread index equals 0, so the first thread 0, then you take your value x, which is your private variable to that thread, and then you write it to this shared memory space array. And then you read it again if you're thread 1, you read into your private variable x the copy that exists in this shared space. But in order for this to work right with a race condition, you need to make sure that the threads are that the write is done from thread 0 before the read is done from thread 1. So you can use this sync threads call, which will basically just make sure that all threads wait at that point for all other threads within the block. Okay, so there's quite a lot you can do within each thread of blocks, but it's not possible to communicate between different blocks in a kernel. Okay, so if you've got multiple blocks, then these can't communicate with each other. And the reason is that the system wants to be able to schedule these as it sees fit, so they may be scheduled in any order. So within a single kernel call, it's not possible to pass data between different blocks in that kernel. What you'd have to do is exit that kernel to get a synchronization point and then start a new kernel. Okay, and we're almost done now. How do you actually get CUDA code compiled, etc.? Well, with the CUDA distribution, there's an NVIDIA compiler, NVCC, and you just use that as you would any, like for example GCC. There's some extra. Have a look at the man page, etc. There's some extra flags that you probably want to put in practice, like the optimization, and also to specify which GPU you're compiling for. There's a question. Okay. Okay, so we have a question. Can you load multiple different kernels onto the GPU at the same time? The answer is, with the latest GPUs, yes, you can, depending if they're set up properly. So traditionally, what would happen traditionally with the GPUs is that you could launch multiple kernels at the same time, and they would all then be queued up for execution in the GPU. You could even have different codes on a server that launch kernels on a GPU, and the GPU would just schedule these and do them in turn. With the newer GPUs, then they can actually, if they think they have space on them, then they will actually try and execute multiple kernels at the same time on the GPU. And there may be a performance benefit from doing that, although it may be better just to have them queuing up. Okay. Okay, so to summarize, GPUs offer performance advantages over CPUs, but you can't just compile your standard CPU code and have it run immediately or automatically on the GPU. And CUDA allows you, it gives you the extra syntax you need to get your code running on the GPU. Traditionally, CUDA is for C and C++, but PGI provide a commercial Fortran version of CUDA, which is very similar. And we introduced the key CUDA concepts and gave examples. Okay. So that's the end of this introductory lecture, but as David said, we have plenty of time for questions. Okay, question coming in. How slow is the memcopy function from device to host? So it's several times slower than, so the important speeds in the system are the bandwidth from the GPU memory into the GPU, okay, and obviously how fast the GPU can compute. But compared to the bandwidth of the GPU memory, it's maybe some order of 10 times slower, something like that. I don't know exactly. You can look up. It's basically it's the bandwidth of PCI versus the bandwidth of graphics memory, but it's quite a few times slower than the memory into the GPU. So it's really a bottleneck if your code is waiting on these transfers. What you want to do is you want to try and make sure that for your simulation or calculation that you keep your data resident on the GPU as much as possible. Okay, so if you've got, for example, you have a time stepping code, you want to keep your data on the GPU across all the time steps and only copy the data ideally at the start and then back again at the end. Of course, if you have, for example, a parallel code that uses multiple GPUs, you might want to have to copy data to do halo swaps, etc. for MPI. But in that case, you want to restrict the data transfers to only those elements, for example, the edges for a halo swap that you need. So this is one of the key things to try and minimize the amount of data that goes between the device and the host. Yeah. Okay, any more questions? Okay, so we mentioned oversubscribing threads onto the cores. Is there any rule of thumb how much? So yeah, if you look at how many cores are on a device at the moment, the high-end devices, there's maybe 1,000 cores, the order of 1,000 cores on the device. So you would probably want to have tens or hundreds of thousands of threads. So yeah, 10 to 100 probably would give you good performance. If you have, if you had, as I say, the same number of 1,000 threads, then that's the same number of cores that you would probably end up being hit by memory latency issues. But again, it really depends on your code as well. I mean, some codes, if you're lucky, then you can keep your data. If you can keep your data, if it's can be cached on the on-chip memories on the GPU, then you won't need to access the global memory and you won't be hit by these latency issues. So it may be that your code is lucky and you can get good performance without oversubscribing too much. It really depends on the code. But typically I would try and get you 10 times at least more to get good performance. Yeah. Okay. Any more questions? Well, people are thinking about questions. I'll also mention that there's an online. This lecture will go online on the Archer pages, but there's also another space from the EPCC training pages that you can get to, where I've put up. I mean, I did this about a year ago, so it's an older version, but it's essentially an older version of this lecture with a little bit more in it, called Learn CUDA in an Afternoon. I'll just type that into the. If you Google this, you should find it. And again, it's available through the EPCC training pages, or it's on YouTube. And it's me giving a version of this lecture, but there's also some practical exercises that you can download and do if you have your own access to a GPU machine as well. And the lecture goes into some optimization details as well that I touched on very slightly. It goes into more detail on those.
That's a good question.
Yeah. How standard is the Fortran interface compared to C? Well, it's standard in the sense that there's only one vendor that provides it, so there's no, it's just provided through PGI, so there's no other versions of it. So that is the de facto version, if you like. But it's, as I say, it's been developed to be very closely similar to the CUDA C. So I think it is, yeah, I think it's fairly standard. And as I say, PGI are actually part of NVIDIA now, so I think you could probably treat it as being as standard as CUDA, given that CUDA is an NVIDIA proprietary programming model as well. Okay, so for parallelizing computation, it doesn't need communication between threads, the vector add. How do you balance the number of blocks per thread? Okay, so again, if you do the practical exercise that I mentioned, then there's an exercise where you look at this, and what I would always do is choose, as I say, that the number of threads per block is almost always best to be a small multiple of 32, which we call the warp size. It's an architectural feature. It's called the warp size is 32. So we always have the number of threads, a small multiple of that. So what you would normally do is experiment with the number of threads per block as being, for example, 64, 128, 256, 512, 1024, and then the number of blocks will be determined by your problem. How many overall threads you need is determined by your problem, so you just have to divide the number of blocks by the number of threads that you're experimenting with and measure performance. NVIDIA also provides something called an occupancy calculator spreadsheet, which gives you some hints, and you can play around with that and see if it can help you work that out. But it's very problem dependent. It's different for each problem because it depends how much resource each of your blocks uses. For example, if you have a block that uses a lot of registers, then that will limit the total number of blocks that can run at the same time as each other. Whereas if your blocks don't use many registers, then the system may end up scheduling many more blocks to run at the same time as each other. So it's very dependent on the problem. Okay. Okay, I don't see anyone else writing, so if anyone's got any last questions, it's measure time. Okay, I think we'll finish up there then. David, do you want to say anything?
Yeah, so I'd just like to thank Alan for giving the talk. That was very useful. And just to say, we'll be carrying on the virtual tutorials into next year. The standard date is the second Wednesday of every month at 3 p.m. Like this one was. I hope you found them useful. As I said, the recordings are available online if you just go to our training, ArchRacer UK training virtual, you'll see there's obviously the link for this tutorial, but for a lot of the tutorials there are recordings available. So we, subject to technology glitches, we hope to have these recordings up there. So I'd like to thank everyone again, and hope you'll have a good Christmas.
Okay, bye-bye.